Hello, Tanya Laird here, and welcome to part 1 of Lecture 14 of ENGR 231 Engineering Statics. In this first portion of Lecture 14, I just want to discuss a brief introduction to centroids, discuss what centroids are, look at some basic formulas of centroids, and some of their related properties. So first of all, I would like to look at centroids, and really this portion of the lecture is really looking at the theory of centroids. So centroids is a very generic topic. Centroid is the term centroid is a very sort of far-reaching topic, or broad topic, I should probably say. And so for a centroid, if I were to give a uniform definition of a centroid, I would say something like a centroid is an average, or is the average location of some property across a body or surface, or I should probably say cross section of some property across a surface, body, or cross section. So one you're probably familiar with from perhaps previous courses and things like that is center of mass. A simple example of a centroid is a center of mass. So for example, let's say we have a simple xy coordinate plane, and let's say I have a 1 kilogram mass and a 3 kilogram mass, and some distances here. Let's say this is from the y-axis to the 1 kilogram mass is, well, I don't want to use 1 meter, that's redundant, so maybe 2 meters and 4 meters, something like that. Actually, that looks more than twice the distance, maybe 6 meters here. So the center of mass, the x-coordinate of the center of mass, we could calculate that relatively easily by just a weighted average. Let's see, just treating each object as a point particle, of course. The x-coordinate of center of mass and you may remember this from basic physics, either university physics, college physics, or even something like this would be a problem as simple as this would really be on the level of even a high school physics course. The x-coordinate of a center of mass, or of the center of mass of this system, well, I would say, okay, let's see, I would say this is 1 kilogram times 2 meters, basically just a weighted average again, plus 3 kilograms times 8 meters. That's basically the x-coordinate of that 3 kilogram mass, and then divided by the total mass of 4 kilograms. So what would that come to? That would be 2 plus 24, 2 plus 24 divided by 4. So 26 over 4, and that would be 26 over 4, and lazy sight. That would be 6.5 meters, of course. And it's no surprise that is closer to the 3 kilogram mass than the 1 kilogram mass, because because the 3 kilogram mass is much larger than the 1 kilogram mass. So, in the case of a center of mass, what we are doing is we are averaging mass, and that's the property that we are averaging. The property in question is mass. So we are averaging mass across a geometric area. So you've probably heard of centers of mass before, but centers of mass are specific to mass. They are talking only about the distribution of actual mass or mass energy across a plane or a volume or whatever it might be. Sometimes in your in your calculus classes, you might have even much more complex examples of this. So, for example, you could have a three-dimensional body that would be like a more. Let me just illustrate something like this: a more complex center of mass. Center of mass problem. So that was a simple point particle type analogy, or a simple point particle problem, but you could definitely have more complex ones. A calculus 3 type problem that you might see in a, well, I guess in a Calc 3 course would be something like this. If you had an object of varying density, and I could actually draw it as, just a very complex 3D object, and then I would describe it via some equations or something like that. This is meant to show sort of like almost like a wavy cube or wavy prism or something like that. And you might have some object that would say, okay, the rho of this object is some function of x, y, and z. So you deal with some object that is not a constant density. And to actually solve this one, you'd have to do this by integration, and you would apply a center of mass. Basically integrate the center of mass formula. Center of mass, or I should probably say integrate the density across the volume to get the center of mass. Well, not just literally across the volume, you'll have to multiply, basically treating each dx, dy, dz as a small particle and then integrating therein. All I'm trying to show is that you can extend the same kind of basic point particle. This is very simple, this is very intuitive, but you can extend it to even objects of much greater complexity. Like imagine if you had an object that, let's say it linearly increased in density from the left side to the right side. There are mathematical techniques to average that increase in density, and that would actually be very strange. I would be curious what kind of material that thing was actually made out of. That would be very hard. Actually, I mean, think about actually building a physical object that was a smoothly increasing density from the left side to the right side. That would be very difficult, but I suppose a particularly clever engineer might be able to figure out a way to do that. But anyway, you can describe things mathematically that are far more difficult to actually create in actuality. So you could describe some object that has that is existing in certain bounds and has a density that varies with x, y, and z, and you could integrate across those bounds to get the actual center of mass, etc. But that's a three-dimensional example of the center of mass. But centroids are a much more broad term. So if I were to create a Venn diagram, consider a Venn diagram as shown below. Centroids are a very, very broad and generic topic. So you have you have this term centroid, and maybe I could break this down into 2D centroids and 3D centroids. Although all the things underneath these are 2D and 3D, so maybe I'll just do some overlapping circles as I'll show below. So all of these are centroids, and one primary major area of centroids would be centers of mass. That's a major category of centroids, and those are very important, especially for dynamics problems. But you can also have centroids of area, and that's what I'm going to focus most on in this lecture, because honestly, in terms of most areas of mechanical and civil engineering, at least in terms of beam design and torsion and things like that, centroids of area are typically the most important. But you can also have things like centroids of pressure, of force and pressure. We'll see this, or if you take a mechanics and materials course, you'll see that there. Centroids of force and pressure. And if you get into things like electrical theory, gravitational theory, things like that, you can have centroids of electric, gravitational fields, that sort of thing, or electric fields, gravitational fields, etc. Or maybe like potential, fields, etc. You can deal with centroids in terms of, many different things, etc. And these also will, all of these things would be applicable in either 2 dimensions or 3 dimensions. Although, truth be told, in this class, we're going to focus mainly on the 2D applications. So maybe I could do something like this. Within each of these are 2D examples and then 3D examples. 3-dimensional. So centers of mass, again, is dealing with the, if I were to define a center of mass, how would I look at that? Or what would I say that is? A center of mass is effectively just the average location of the mass of an object. It's kind of just in the name. It's what's written on the box, essentially. The average location of the mass of an object. So back to this example here with the 2 very simple point particles. If you were to do just a basic, or not basic, but well, each step would be basic, but the actual, trying to do that by hand, or not even by hand, even with the computer, the calculations would be just impossibly complex. Imagine if you could do the same sort of thing in 3 dimensions rather than 2 dimensions. That's not particularly hard. But imagine instead of doing it for just 2 particles, you did it for literally every single atom in a bulk object. Like, you know, if I drew like a, I don't know, like a simple object, like a pencil or a cup or something like that. Consider a cup. I have a water glass in front of me. So imagine something like a cup. This is nothing more, at least conceptually, nothing more than a very, 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 very convoluted case of this. Well, actually, we simplify it when we actually calculate it, but we simplify it by using area methods and volume methods, etc. But if I wanted to actually calculate the centroid of this cup, conceivably at least, I could do it using nothing more than this particle-based approach. What I would have to do is, if I knew the exact location of every single atom in this cup, and, so this is sitting on a surface, oh, if I can draw my surfaces properly. This poorly drawn glass is sitting on this surface, and if I knew the exact mass of every single atom in that cup, and I knew the exact position of every single atom in that cup, I could just basically do the exact same thing. A sum of forces in the x direction, basically a sum of forces, if I want to get the center of mass in the x direction, I could just multiply the x coordinate of each mass times its own mass, and then divide by the total mass. So if I were to get if I were to try to do the center of mass particle approach, the x bar, the x coordinate of the center of mass, and maybe I could put a little m here for center of mass, would be equal to, this would be the summation of the x times the m of that particular mass divided by the summation of mi. So again, if I could somehow, to try to do this actually in reality would be absurd. You'd have, well, Avogadro's number 6.02 times 10 to the 23rd. So that describes the amount of matter in the approximate order of magnitude of the amount of matter in basic objects. So, even objects measured in, grams and kilograms have an absolutely absurd number of individual atoms. So trying to apply this formula to a macroscopic object, an object you can hold in the palm of your hand, or you can see with the naked eye, is absolutely absurd. Even trying to apply this to something microscopic like a cell or something would be absurd. You can't apply this, but you can't apply the summation, but you can apply continuous forms of this using integration. And y bar m would be the summation of y mi divided by the summation of mi. Basically, again, all we're doing here is summing up the y coordinate of each mass times the mass of that individual particle. And we could look at this in 3 dimensions as well. Zm is equal to the summation of z, the z coordinate of any given mass, times the mass of that object, or that particle, or that atom in this case, or I guess we could also say molecule, divided by the total mass of the object. This is basic center of mass. This comes from elementary physics. But honestly, in statics, we're not necessarily totally concerned with, especially in engineering design, like mechanical engineering and civil engineering, when it gets to beam design and the design of rotational systems like drive shafts and things like that. We're not so much concerned with the center of mass. Often we're concerned with like the center of area, or center of volume. Or I should probably, if I'm going to finish up with center of mass, I should mention there are also integral approaches. These formulas describe how you could sum up individual atoms or particles. In practicality, obviously for real physical objects, anything that you can actually see with your own eyes, it's not possible to add up the individual masses of every single atom or molecule in an object. That's just not, you're dealing with like 10 to the 23rd level of approximately that order of magnitude, maybe a couple orders of magnitude up or down, but you're dealing with that number of objects, and try to calculate all those with even the most powerful supercomputer on Earth, let alone do it by hand, would be impractical to say the least. But really, when we do integration methods, it's just a continuous and simplified form of this. Instead, we use integration forms. Or integration methods if the objects cannot be broken down to a series of simple point particles. Be broken down or summarized, or I should probably say summarized, as a series, or probably not summarized, approximated as a handful of point particles. So for example, when I say summarized, I'm referring to something like this here, a 1 kilogram mass and a 3 kilogram mass. Even ignoring that atoms aren't true point particles, obviously a 1 kilogram mass, that's like 2.5 pounds, obviously a 1 kilogram mass isn't made of a single atom. That would be a terrifyingly massive atom, and I would have no idea how you would create such a thing. And if you could teleport if you could magical genie wish a 1 kilogram single atom into the room that you're in, you would have a very bad day indeed, because that would basically be an unstable atom, and the entire atom would rapidly decay into some horrible swarm of subatomic particles, and all sorts of energy would be released, and that would probably take most of the city that you're in with it when it broke apart. So let's not worry about it. So obviously a 1 kilogram object or a 3 kilogram object is not a single point particle, a single atom. This is something like a, bowling ball is too large, a baseball is too small, but an object weighing in a couple pounds, or 1 kilogram or 3 kilograms when you're talking about mass. And each one is made of multiple, or not multiple, but almost countless atoms. Although using chemistry principles, you can of course actually calculate the approximate number of atoms in an object. But when I say that an object can be treated or approximated as a single point particle, I'm talking about something like, if I want to find the example, if I have like spherically symmetric objects, for example, if I have a baseball here, or a sphere of 1 kilogram here, and a sphere of 1 kilogram here, you can actually just approximate those as 2 point particles. Those are things that you can just approximate. They're not actually single particles, but you can approximate them as such. So if your system is that simple, yes, you can just use this simple summation technique. But in more complex objects, you're going to have to do an integration-based approach. And I'm going to demonstrate that integration-based approach for area, but if you look in the text, you can actually see those approaches, integration approaches for center of mass as well. So typically, for more complex objects or systems, they cannot be approximated as just point particles. Rather, integration approaches are needed. And I'm going to introduce two terms. Well, actually, I should back up and say I'm going to discuss these topics primarily in using the area-based centroids approach. So, in this lecture, we will primarily focus on area centroids. Because these are a very useful way of demonstrating the basic math behind centroids. There are, of course, as we discussed, many other forms of centroids. Center of mass is a form of a centroid. You can talk about centroid of pressure. You can talk about centroids of fields, etc. Primarily on area centroids. So you can have centers of pressure, center of force, etc. And in fact, in this course, we've actually seen a case of a centroid or of centroids where they're not either center of mass or centers of area, and that would be our basic distributed load or line load. So we've seen previously that the center of mass of the centroid of a area load, a line load, if this was, say, like, I don't know, this is W in kips per foot, for example, the centroid of that area is 1/3. If this whole thing is L, the centroid of that is 1/3 from the base, or L over 3, or L over 3. And we've already applied this this formula before in some previous lectures, lectures 10, 11, and 12, when we looked at approximating or working through working through the equations of rigid body equilibrium on trusses and frames, as well as calculating internal shear and bending moment, or internal forces, I should say. So we have already seen gained some exposure to forms of centroids that are not just centers of mass or centers of area, but in this particular lecture, I want to focus on centers of area, or centroids of area. So a centroid of area is basically exactly what it sounds like. A centroid of area is the average location of the area of a shape. Of a shape's area. And what I mean by that in particular is when I say area, typically I'm referring to cross-section. At least in most civil and mechanical engineering applications. So for example, let's look at some basic, I'll look at this in terms of some basic steel shapes. Let's say you had a wide flange shape, and it's a wide flange shape that is symmetric about both the x-axis and the y-axis. So let me show you this. Let's show the axes. Maybe I have an x-x axis here and a y-y axis here. If I can manage to draw some dots properly. And a y axis down the middle. For this particular shape, for a shape that is doubly symmetric, the centroid is just going to be right in the middle. So the centroid would be right there. Again, where this would come about is that, and I think it's fairly intuitive, that the centroid of an object that is symmetric in both the x direction and the y direction is right at the shape's middle. But if you want to think about this, imagine dividing this into little tiny bits of area or little small point particles. If you did that same exact x and y coordinate times the area as we looked at with center of mass, you would get the same location. Or we can also have more, the same sort of thing persists. We can also look at centroids for non-symmetric shapes or non-doubly symmetric shapes. For example, let's say we had a T-section. A T-section sometimes is made by literally sawing one of these in half. So let's say we had a T-section like this. So now this is symmetric about only a single axis. This is only symmetric about the y-y axis here. but it's not symmetric about some other axis. And so maybe this, let's say the centroid of area was here. Maybe I define that as my x axis. And my centroid would be, again, in the center of the y coordinate, but it would not be in the central coordinate of the center coordinate of the y axis. Or so I should say it'll be at the 0 point of my x-axis, but not at the 0 coordinate of my y-axis. It's going to be shifted, in fact, maybe I'll, well, that's fine. It would be shifted up a bit from the halfway point. In other words, the distance from here to here would be less than the distance from here to here, because there's more area, there's a lot of area in this top flange here, and less down here, so it would have to be shifted a bit upward. And then you can also have shapes that aren't symmetric about any axis, at least any vertical or horizontal axis, like this, like a L shape. And here the centroid of area would be something like this. The centroid of area for an L shape is going to be something kind of like this. It's not symmetric about the x or the y axis, so it would be about there if you run through the integration. So how do you actually find this? How do we actually go about finding the centroids for area? Well, first I need to introduce a topic or a quantity or definition called the first moment of area. The first moment of area fundamentally is the integration of the x-coordinate of a differential element, or I should say the coordinate of differential element, because we can also have one, we can have them in either with respect to the y or with respect to the x, is the integration of the coordinate of a differential element times the area of that element. And when I say differential element, I'm really coming back to calculus and referring to either a dx or a dy, an area created either from a dx or a dy. And so, again, let's say you have a body, or just a cross-section, or a shape, and you want to find the first moment of area. Well, if I was doing the qy, I could use an element like this, with a dx and an x-coordinate from, or a coordinate in x from the y-axis. So, the first moment of area with respect to WRT, the y-axis. Again, what I'm doing here is basically backing up. What I'm effectively doing here is doing a weighted average, but except a weighted average by integration of the x-coordinate of each component or each piece of that area times its actual area. So qy, the first moment of area with respect to the y-axis, is equal to the integral of x dA. Now it's very tempting, actually, as I almost flubbed up there, to say, oh, qy, that goes with y. I mean, there's a y that should go with y, right? Well, no, because we're measuring, effectively what we're doing is, for the qy, we are measuring the distance from the y-axis, and that distance is measured via a x-coordinate. And then, the first moment of area, with respect to the x-axis, is going to be just a very basic modification of this. Qx is equal to the integral of y dA. So fundamentally, this qy is telling me a weighted, not necessarily yet a weighted average, but basically if you could add up all of the particles, individual atoms in this shape, in this cross section, and multiply the x-coordinate of each times the area of each of those particles, you would get the qy here instead of mass or dent area. It's basically an integration of the dA basically here is this coordinate here, or this piece here, this dA, and we're multiplying the x-coordinate of that piece from from the y-axis to the center of that shape, or the center of that slice, and then just integrating across that. Okay, and then once you have those, getting the actual coordinates of the centroid is relatively easy. Area centroid. The hard part really is the integration. Centroid. Well, the x bar is just going to be qy equal to qi divided by a, or the integral of x dA divided by the integral of dA. The integral of dA is just going to give you your overall area, and y bar is equal to qx divided by a, and this again is sort of a weighted multiplier of the amount of area, how far you are from the x-axis. So qx is equal to the integral of y dA, or the integral of x dA. Again, x does not go with x and y does not go with y in this case. And so that would be the integral of y dA divided by the integral of dA. Or if you can just if you already have the area of the shape, you can just divide by dA. So how do you use this? How do you use these formulas? Well, in this lecture, we're concerned primarily with, in this particular lecture, lecture 14, we are primarily concerned with solving for centroids directly by integration. So we're dealing with shapes that are relatively simple and things that we can directly integrate. So one, how to use these formulas. One, construct a differential element. Essentially, if you have if finding qy, you need a vertical element thus use a dx. So if you are trying to find the centroid of just a curve like this, you would have a dx here, and then some value for the height. In this case, this would just be like the function value as the value of the function at x, and then you'd have a distance from the y-axis of just x, or x bar. Sometimes you also see it described as x bar in textbooks. But there's, of course, innumerable ways to describe these things. And again, it's important to realize that qy describes the integration of area, basically asking how much mass do we have, how far from the y-axis. And that is why we use the x-coordinate with this, because knowing how much area you have, how far from the y-axis, will allow you to determine the x-coordinate of the center of mass, or in this case, the center of area of the centroid, or the centroid, I should say. If finding qy, the first moment of area with respect to the y-axis, need a horizontal element. And this horizontal element would be something like this. So you'd have your function, and you'd have your differential element here. This would be your dA. And so if finding qy, you need a horizontal element, and you would be measuring a y-coordinate from the center of mass here. The distance from the x-axis is measured in y. It is the distance from x is in the y-axis. Okay, so once you have those, what do you do next? If finding qy, you need a horizontal element. So the first thing is we construct a differential element to set up the integral. So you're going to have something like qx is equal to the integral of y dA, and dA, if we're using this example here, or this diagram here, your dA would be like this element here, and let's say you just have some f of x, your dA, actually no, I should say, sorry, I wanted to make this with respect to the y-axis, so this would be equal to x, the integral of x dA, and so you'd have an f of x. And if you look at this differential element here, or that slice of the area under the curve, we have a dx, a base width of dx, and a height of f of x. So therefore, dA, the little differential element, is equal to f of x times dx. And this dA is what you plop into your formula. So for this case here, it would be equal to the integral of basically x times f as a function of x, the y value is a function of x, times dx. Then once you set up the integral, it's simply a matter of working through the math here. The integration and centroid formulas, to obtain the centroid of the shape. And that's the basic idea, and we will look at it in, we will look at some examples in part 2 of this lecture. So again, x bar, the average location of the area in the x direction, will be equal to the integral of, let's see, qy is equal to the integral of x bar dA, or just x dA. So that'd be equal to x dA times, again, x bar dA divided by the integral of dA, or just divided by the area. And y bar is equal to the integral of y dA, or in other words, qx here, or I guess on the previous page, qx. Again, q is the first moment of area with respect to, so qx is the first moment of area with respect to the x-axis, and then divided by dA. And really, that's the basic method of finding centroids of simple shapes rather than composite areas. We'll get to composite areas in lecture 15. But this is really the basic idea. You have to set up an integral, or you have to set up your diagram first, construct a differential element. Next, you need to set up the integral. Then you need to work through the integration and centroid formulas to obtain the centroid of the shape. And then finally, report the x and y coordinates of the centroid. And don't worry, again, we will see examples of this in part 2 of this lecture. So that describes the basic method of, or the basic theory of finding centroids of areas. And like we mentioned, there are many types of centroids within this class, because those are the most important things for like bending and beam behavior and rotational shafts for mechanical engineers, that sort of thing. The centroid of area is going to be most critical for our analysis. So I think that'll do it for this part of the lecture. Please let me know if you have any questions, and I will see you soon for part 2 of lecture 14, where we will look at some examples of finding the centroids of areas by integration. Again, please let me know if you have any questions. If not, I'll see you soon for part 2 of lecture 14, and as always, thank you.